At the very beginning of this class, we talked about how you want to measure how long an algorithm takes. You have the size of your input, and then you measure how long the algorithm takes based on a function relative to the size of that input. So n or n squared or 2 to the n or whatever it takes. And we wanted to make it polynomial instead of exponential. And I mentioned at that point that we're assuming that we're using a model of computation of a computer, where basically your units of work are moving something from memory to the CPU, doing some addition on it, asking a question, is something bigger than something else? And that's what we measure. And we don't care about constant factors, so as long as we measure, one of each thing in a loop, we're OK. And that was our model. And I mentioned then that, well, you can come up with all sorts of other stranger models that don't use things like computers. And a good example that comes from an old Scientific American article, I think it's by ADUni, but he gave a whole example of computations that don't use computers, just to give you a sense of using a different model. And one I mentioned to you, this idea of sorting. So instead of sorting, by a decision tree where you're comparing things, or by counting sort where you're putting things into slots, we're going to sort in a completely different model of computation. We have a list of numbers and we put them into a machine, and the machine is built so that if you put in a number to the machine and a strand of spaghetti, it will cut that piece of spaghetti down to the size of that number. So you throw the bin filled with spaghetti, and you put in this list of numbers, and out comes pieces of spaghetti exactly equal in length to the numbers that you put in. And then at the end, the machine gathers them together by shaking the spaghetti up, not enough to break it, but just enough to line it all up, and then gets it all with a clamp around it, and slams it down on a table so that all the strands are flat on the bottom and they all stick up. And then one by one, there's a little machine that comes down and pulls the top piece of spaghetti it gets to out like a piece of glue, lifts it, puts it here. Another, like a little circle of glue, comes down, pulls the next one out. So how long does this take? I mean, assuming this machine can cut the piece of spaghetti down, that's its atomic operation, and that the glue thing is an atomic operation that takes one step. Certainly doesn't have to search for the next one, it just comes down and picks the next one up. So it takes linear time to sort the numbers, because you process each piece of spaghetti in a constant step for each number, and then you pull them out one at a time. So does that mean this n log n can be beaten? Well, it's a different model of computation. It's kind of a discussion in a different universe. And that's what DNA computing is more or less about. It's about, let's not think of doing the algorithm with a computer. Let's think about doing the algorithm by leveraging some other natural computation power we have, namely the human body, that does all sorts of very complicated computations very fast, some automatic. All right, so one more notion to make a connection. There's also a notion of a probabilistic algorithm. We didn't talk about this too much in class because they're complicated to analyze. But a probabilistic algorithm is one that is relatively easy to describe, some simple kind of an algorithm that runs in polynomial time, but doesn't always give you the right answer. So for example, you could come up with a probabilistic algorithm, say for the 3-set problem. The algorithm might run in linear time, but when it tells you, yes, there's an assignment, it might be wrong. A good probabilistic algorithm only has a teeny chance of being wrong. And you can do certain things to minimize that percentage. So the hard thing about a probabilistic algorithm isn't coming up with the algorithm, but is analyzing what's the percent of chance that the answer is wrong, if you do the algorithm so many times. And the more you do it, the more accurate you can gauge your answer. Okay, if there's a 90% chance it's going to give you the right answer, you can do it 10 times and then have a better chance of knowing whether the answer is right or not. Yeah. Okay.
Does that presume that it's going to sort of run differently, even on the same input every time?
Yes. Okay. Yes. There's randomness to probabilistic algorithms, so that you have a certain expectation of whether you think the answer is right or wrong, but it certainly will not do the same thing every single time on the same input. It might, but it might not. Yeah. So what we're going to do today is talk about one problem and how to try to solve it using a computer, using DNA. And this research started, I think Edelman was one of the first people to work on this, and he's one of the early pioneers of RSA cryptography, and he started working on this DNA computing in the mid-90s, maybe 94 or so. And now it's kind of evolved, and it hasn't yet come to any successful, stable point. It's not as though people have made great breakthroughs in this area. It's still kind of not known whether this will come to be the great advance that it seems like it might, or whether it's just going to be a peculiar little blip on the radar screen of interesting curiosities. The problem we're going to talk about that can be solved with DNA, at least the first one that we'll talk about, is the first one that was talked about was Hamiltonian path. So you know this problem. You're given a graph, and you want to know if you can get from one vertex in the graph through all the other vertices in the graph without revisiting any one more or less than once and ending in some other particular spot. In this version of the Hamiltonian path, you're not only given the graph, but you're given the place you want to start from and the place you want to end at. So it's the version where you're given the graph and the start point and the end point. So the input is the graph and two nodes, start and finish. So before we get into the details of how you use DNA to do this computation, what you should realize is that this computation is not guaranteed to give you the right answer, the same way a probabilistic algorithm is not guaranteed to give you the right answer. The reason it's not guaranteed to give you the right answer is because the way we're going to use the DNA has flaws with respect to the laboratory. There are errors that can happen in the actual experiment that you would do to solve this. When you actually play around with the DNA strands and you try to put them in the solution and you try to get them to glue together in the appropriate ways, there's some that don't do exactly what you hope. So you try to kind of load the dice in your favor to make sure that 99% of the time the answer is right, but there's always a chance the answer will be wrong. So analyzing how accurate this method would be is a matter for the scientists to determine the error, likelihood in the experiment. Okay so far? All right. The second thing that's going to be a little bit hard is that this actually depends a lot on understanding some basic biology, and that's about all I understand myself, some basic biology. I know what I learned in high school and a little bit in college, and I'll remind you of what you know about it, and maybe Sam Klein can correct us when we get to details about the biology that's beyond the freshman level. But basically, to really understand this problem well and to be able to do this research is very much like doing a reduction between one problem and another. When you do a reduction from, say, vertex cover to Hamiltonian path, you got to be pretty fluent with both problems. You got to have a sense of what both problems are about. You can't just be a complete amateur in one problem and expect to be able to encode one with another. You got to feel like you understand the problem well. And it's the same thing here. What we're basically going to do is we're going to encode the Hamiltonian path problem into DNA strands so that a natural biological reaction will help us determine if there's a path in the graph. So we're going to actually pretty much formally reduce the Hamiltonian path problem to a DNA gluing problem. All right? So in order to do that, you have to have some sense of what are you allowed to do with DNA? What can you do? Because right now it's just kind of magic. So I will mention along the way what kind of things you can actually do, but I think the cleverness and the future of DNA computing depends a lot on the scientists on the other side, of how the technology allows you to do different things with DNA and play with them, not just imagining them as strings on beads, but what you can really do. All right. So here's a little review of what I know about DNA and what we'll really need to know for this problem. DNA's got this doubly helical structure. Two strands of molecules which connect together into one big molecule. And They connect together in particular pairs. There's 4 different components. There's the A and the T that pair together, and there's the C and the G. These stand for adenine, thymine, cytosine, and guanine. Is that from high school? You remember that? From college? Just life. just walking on the street to the post office. It comes up in conversation. All right. These components pair up so that it would look something like this. If I can. And there's another one that goes, oh geez. And they pair up. So an A and a T, a C and a G, another C and a G, another something like that. And they pair up down the line. Okie doke? And they click together. This idea of these 2 strands pairing up is going to be one of the main things we use to leverage trying to model a Hamiltonian path. There's a lot of details about what we're going to do, but the main idea is the fact that these things pair up like that. And they like to pair up. If you throw them in a solution, they go together. I don't know too much of the details, but what I understand, if you throw things in a solution and they start to connect up, that you have to put some other chemical in to make sure those connections actually glue together and stay that way. Otherwise, they can separate and glue up again with some other strand. So when you actually do these experiments, you throw the DNA and you also throw some other chemical in which kind of acts as a glue.
Enzyme-y things.
Yeah, there's I got the name of one of them. Well, we'll get to it. Enzyme-y things. Okay. A little more big picture before I get into the details. We talked about non-deterministic algorithms. Those were algorithms that don't run in our real computers. Those are algorithms that we kind of imagine in our minds work like this. You guess a solution to the problem by magic. And if your algorithm can check whether it's right in polynomial time, that's a non-deterministic polynomial time algorithm. We said if you want to really do this for real, you got to actually try every one of the guesses and see whether one of them works, rather than just being able to try one. So practically, non-deterministic algorithms end up usually getting done deterministically in exponential time. But what if you had some kind of mechanism to check all the guesses at the same time, to do them in parallel, and OR your answers together? If this one or this one or this one or this one works out, then you answer yes. If you had some kind of computation structure to do that, the non-deterministic polynomial time algorithms would run in polynomial time. So that's what DNA is good for. We are basically going to use DNA to make a real-life non-deterministic polynomial time algorithm. We're going to have the DNA model, in some sense, a parallel checking of all the possible cases. We're going to do that by completely overwhelming it with kind of food, and we're going to let it eat, and there's going to be enough food for it to try all the possibilities, and it will try them all at the same time. And we'll see if any of them worked out by fishing through them. More or less, that's it. All right, well, we're done. All right, let's get into the details. So what I'm going to spend time for the next half an hour or so describing is a reduction from Hamiltonian path to what I'll just write DNA, to some DNA gluing problem. So here's what I'm going to do. You give me a graph. You want to know if it has a Hamiltonian path. I'm going to turn it into a bunch of DNA strands, throw them into a test tube, do some things. And when I'm done doing all those things, if there's any DNA left in my final test tube, the answer will be yes. And if there's no DNA left in that final test tube, my answer will be no. Okay, that's the idea. So I need to describe to you what kind of things we're actually going to throw in this test tube and how it works. And it's not so bizarre. Kind of makes sense. Okay, so the first thing you do is you look at your graph and you make up a string of these ATs and Cs and Gs. for each node. The length of that strand depends on how big your graph is. But let's just figure right now that we have a graph and the length of the string for each node will be about, whatever, 20 long. Okay, so for each node, we have a string that's 20 long, something that looks like this. For each node.
The same symbols for each one?
No, no, every node's got its own special sequence.
Is that why we need it to be long enough to cover all the unique combinations?
Well, there's a... Chris asks, is that why we need it to be long enough to cover all the combinations? The reason we need it to be long enough is to kind of guarantee a high probability of success at the end. But if we have just like 10 nodes, we certainly don't need a length 20 sequence. But we have much longer sequences than we actually have combinations of nodes, just to make sure that if they connect, that there's a higher probability that if there's an edge, they'll really connect. You'll see that in a second. Right. So let's just say these are 20 long. All right. We're not putting anything in the test tube yet. We're just setting up our structure. And the actual characters don't really matter. I mean, it's whatever you can do in the lab. Just make sure you have a unique sequence for each one. OK. Next step. Now we have to mimic the edges. For each edge, x, y. Now you're going to do something for every one of the edges. We're going to make a new strand that's 20 long for each edge, but it's a very specific strand. It's going to be the last 10 from the representation of x, last 10 from x, followed by the first 10 from y.
The word for these things, the last 10 what?
Oh, I don't know. Are they base pairs? Bases.
Bases.
No, these are not paired up yet.
So they're just bases. OK. So they're bases. To me, it's just as useful as the word thing, unfortunately, since I don't really know what are they?
So is that the origin that all your bases are
They're
based
small,
on?
They call them nucleosides.
They're small molecules.
Yeah, that have.
That have a sugar base. They have a sugar,
That's the ribo.
and that's the.
I think nucleotides. Ribonucleic acid, I think.
Yeah,
The
they're-
ribose
yeah,
sugar
they're-
is a nucleotide.
And they've got. They're specifically shaped. I think C and G have 2, and A and D have 3 sites that bind together with one another.
That's why they pair up.
Yeah,
OK. They got carbon in them.
they do.
Yeah, we all.
Phosphorus. And
There we go.
Amino acid molecules.
None of those elements over 100 here. Just
How can you guarantee that the latter half of one is going to, the end of that is going to be compatible with the end of the first half?
oh, as far as I know, Chris, you can take any of these things and string them together in a long, long chain.
Oh, okay.
These are one of these chains, one of these helical things. So when you get actual DNA, you get 2 of these strands that pair up and lock together, and then they curl up like this.
So they pair according to those matching.
They pair according to AT and CG, or GC and TA. But right now, we're just doing one strand. And I think, as far as I know, that there's no limit to what goes in what order and how you connect them. It's like a chemical sewing kit.
Do you have to be concerned that the 10 are unique? So that the first 10 of everyone is unique, so there's not...
Yes. 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 This is long enough so that it would always be the case. This is much longer than... The number of the 4 to the 20th possibilities here is much bigger than the graph. You might use a sequence of 20 for a graph of size 8 to 10. So you're virtually guaranteeing uniqueness here. But it's an important point that as we go for bigger and bigger problems, we'll have to use more and more DNA, and we'll talk about that later. All right, so you create all these edges, and here's the idea. Let me give it to you in advance. we're going to put all these edges in the soup. Okay, in a little test tube with some water and some salt and some enzyme glue. All right? They're sitting there. And then what we're going to do is put in other DNA strands that will help these edges get glued together. In particular, if you're looking for paths, you want to let an edge UV, VW, you'd like to let the strand that represents UV and the strand that represents VW to connect, to get glued together. How do they get glued together? They're going to get glued together. Let's look at this one. This one has what at the end of it? The first 10 from V. This part is the first 10 from V, and this part is the last 10 from V. Okay? The edge that represents UV, at the end of it, the second half of it, has the first 10 symbols from the node representing V, and the strand that represents the edge VW, at the beginning of it, has the last 10 symbols of the node that represents V. So all we have to do is throw something in that's going to match up and sew these two together. What are you going to throw in? The complement of the V node. That's why we did this in a stack kind of a backhanded way. We put the last one first and the first one here so that when we connect edges together, the end ends up being the first half of that node, and the beginning ends up being the last half of that node. So now if we throw into the soup the complements of the node representing V, it will swim around smelling for these two UV, VW, lock on and connect UV and VW together and get a longer strand with a little glue connected on top. Yes?
Tim, you have, let's say only 3 matches. So if you only have a couple coming in like that, can it still glue together? I don't know, just remember. Yeah. Well,
yes. There's all sorts of gluing that might happen inadvertently. Yeah. What I'm describing here is gluing that will definitely happen because there's a big overlap and you expect this. But there's all sorts of other gluing that will happen that do not represent paths that we care about. This is one big, it's a gumbo. That's what it is. Chris brought in a gumbo yesterday. That's what it looks like. It's DNA gumbo. But we are going to make sure, and it's not too bad of an analogy, that we put some special ingredients. So you really love mussels, and you color them blue so that when the gumbo's all done, you can pick out those mussels quick. That's what we're going to do here. We're going to end up...
Why would you?
Why would you? Or you color the mussels blue so you can chuck them in the garbage. That's it. You want to end up getting the DNA that represent paths out of there. You want to focus on them. Not only just paths, but Hamiltonian paths. And we'll get to that in a second. I haven't quite finished this, but I'll get to it in a second. Yeah, Chris?
Well, do you need the original nodes? Are they doing anything yet?
Oh, yeah. We haven't talked about them, and they will do something. I'm not done with the reduction yet.
Okay.
I'm giving you just the big picture. The big picture is this gluing of the complements connecting edges. That's the main idea. That's the way to connect a computational problem on a graph to something that DNA can do. Now, a side point, but a really important point. If you're starting to think, okay, well, DNA can do this, it almost seems natural. I mean, what do they do except connect? So it's kind of like a path problem. But how could you do vertex cover with DNA? How could you do 3-sat with DNA? How could you do knapsack with DNA? It turns out that people have proved that DNA as a tool is a universal computer. If you have any algorithm you want to implement, you can turn it into a DNA program. And that's a difficult proof and a tedious one as well. But that just means in principle that we can always somehow convert our problems to DNA. We just have to figure out a good way. Right? But admittedly here, the two are very intimately related. Okay, so let me just finish the description here. For each node, we set up this instruction. But now in the we'll call it the soup. Here's the soup. Yeah.
You're gluing edges together if they share a vertex, right?
Yes.
They share a node.
Yes.
So, I mean, 4 edges can share a node, or more than 2 edges can share a node, right? So how would you? Seems like you could. This only lets you glue pairs of edges together.
Well, if we had another one, WZ, then the W glue
If you had a VZ,
He's suggesting VX.
A bunch of nodes around a single node, they all connect with a
But
star.
those can't be in the Hamiltonian path.
but they would glue up here.
right. That Chris is asking, can't I get other things that are going to glue to the same spot? Well, first of all, I'm not sure you can have 2 things gluing to the same spot. I think once it's paired, that's used up. But, and I don't know the biology to know for sure, but
I'm talking about in a graph. In a graph, you can have a hub with spokes coming out to a bunch of different other nodes.
sure.
And would you not be able to model that with this? Or?
Sure. We're going to... Oh, I see what you're thinking. I think I do. You're imagining that there's just one of these edges in the soup.
I'm trying to figure out how you would model a whole bunch of edges that all fit into one node. Yeah. Right. 'Cause you can,
You're wondering about this.
Yep.
So there is an edge UW in the soup. There's an edge UX in the soup, and an edge UI in the soup, and an edge UV in the soup. In fact, and I'll say this, I'll write it on the board in a second, there's lots of these edges. You're putting in 10 to the 9th copies of these edges. There's tons of them. That's going to let us do it all in parallel. We're just going to let all these things sit in the soup, lots of them, so they'll be able to find each other. Okay, so if you want to have UV and then VZ connect together, there's lots of UVs, and they can glue with VZ. There's lots of UXs, and that can glue with UV. So what exactly do you feel is missing from...
How you can glue UV to UX and then still have a part of the complement of U available to glue U
UI to UW?
to it. Glue them all together into one graph.
You can't. We're not trying to glue graphs together. We're trying to, and specifically we don't want to. That would be bad. We want to make sure that our DNA glued strands that get longer and longer actually represent paths in the graph.
Not the graph. We're not modeling the graph.
No, we are not trying to get the DNA to look like the graph. We're trying to get the DNA to move together to represent paths in the graph. But your gut instinct to be skeptical and wonder about this is good, because pretty soon you'll think of it and you'll come up with an example of these glued structures which do not represent paths. But we'll get to that in a minute. Okay. First, let's finish the soup. The soup is these edges with the last of the X and the first 10 of the Y. And then, for each node, except the start and the finish, there are exceptions, but for each node I'll write except S and F, start and finish, except the start and finish, add in the complement of those nodes. So this part here is not sitting in the DNA. It's just for our reference on a piece of paper. In the DNA soup comes the representation of the edges and the complements of that list. We have to deal with the start and finish in a second. We'll deal with how it connects in a second. Yeah, Chris.
Add the complement in again, or that was the same step that created the edges?
No, the edges are different from the complements.
So you used complements to create the edges,
No.
didn't you?
No, the edges go directly to my list of bases for the nodes and take the last 10 bases from the node representation of X and the first 10 bases from the node representation of Y, not the complements. And then I could do the complements and then throw in the nodes. I think it would be equivalent, but I just did it this way. All right, clear enough? Yeah. Okay. Okay so far? So right now, if we throw all this stuff in a soup along with some salt, water, a little baking soda, so you throw it in the soup and they start gluing together. And you put in this little enzyme that will keep the connections steady. So now you can find them and they won't break apart when you fish them out. All right. We haven't represented the start and finish at all. So they're done a little bit differently, but not too differently. And I'll write down how they're done And then we'll talk about what's going to happen in the soup.
We don't necessarily know the start and finish.
Oh, no, we're given that.
But we are.
In the version of this problem that we're discussing, you're given the graph and you're given the start and the finish node. There are different versions of Hamiltonian path. The normal one is you're just given the graph and you're asked, does it have a Hamiltonian path? But there are other variations where you're given the start and the finish node. They're equally hard. It doesn't help to be given the start and the finish node. But here we're using the variation where you're given the start and the finish. So here are the rest of the things we have to handle. We need to handle edges that go from start to something else, and edges that go from something else to finish. These edges look a little differently from the others because we don't want these edges we want them to be terminating points. We don't want the DNA at the beginning of here to glue with anything to the left of it. We don't want the DNA at the right end here to glue with anything to the right of it. Okay, all the interior edges are fine. So when I say for every edge xy, these are except the start and finish. Do something different with the start and finish. All right, so this isn't so tricky. How would you encode an edge start x if you didn't want the left end to glue with anything?
Non-binding basis for the first 10 elements in the edge.
Okay, but how do we guarantee it's non-binding? That might be hard. We want to have something at the beginning that's not binding and something that at the end that is binding. So at the end we're going to do the same way. The x should be done the same way we do the end of any edge, which means we're going to use the first 10 from x. So the second part of this is the first 10 from x. And that allows the complement of x later on to glue this x to other x's, which will start with an x, which they have the last 10 from the x. So this will allow the normal glue. The question is, what should the beginning be?
We take all start.
That's actually what we really do. We just use all 20 of start. And that kind of guarantees this not binding thing that you mentioned, Doug. That guarantees that it's not going to connect with any glue because it's too long. Okay? We'd expect the last 10 to show up here, right? But the last 10 are now in here, so we're not going to get the binding that we normally get.
Or you could have made x be a palindrome, the start be a palindrome, so the first 10 are identical to the last 10 in reverse order. It doesn't matter which way you look at start, you're only going to pick up 10 of it.
But then it'll fold up and move itself.
Oh, okay.
Would it? Yeah? Oh, cool. All right, in y finish we do something similar. What does it look like? Who wants to guess?
All 20 of
All 20 where?
the last.
At the end, use all 20 of finish. And at the beginning, the last 10 from y. Last 10.
30 long instead of 20 long.
Right, so these are different. These are 30 long instead of 20 long. They're different, right?
I don't exactly see why you had to worry about the start and the finish binding to anything if you...
That's a good question. Erica asks, why do I have to bother having these little terminating beads on the end if I don't throw in the complements of start and finish? I don't know.
No, the degree might be more than one of the start node.
Right.
So in which case, there might be other vertices which have that sequence. But you don't want it to stick.
Wait, say that again, Sham. I'm not sure I followed you.
You could have, the start vertex might have, if it has just 1 degree, then you're fine, because you won't have a sequence which will match to that.
Right.
If it has 2 or 3 degrees, then there will be other edges
I mean, if there's 2 or 3 edges,
which have that sequence, and they can match up to that guy. And you don't want those edges to match up. They are regular edges, and they keep continuing this strand.
yeah, but Erica's not saying leave it out. She's saying just use 10 like usual.
Right.
So that's going to be a problem?
Because that 10 can match up with, you might have 3 different edges which have those 10. because all those edges are coming out of this particular node.
You might always have that, but it would seem to me improbable if it's 10 long or 20 long. We're not guaranteeing 100% of the time.
Yeah.
We're making these strings up, so.
Yeah, but it'll go on forever then. We have to stop the strand from growing, even if it's the wrong answer.
Oh, that's true. That's a good point. Yeah.
And then you'll have everything stuck in one thing.
Right, right. There is this probabilistic idea that we're not always going to get pure paths here. There's going to be a lot of issues along the way. But also, we do want it not to just keep going here and get longer and longer. Well, you'll see later. Actually, later on, we will cut out the ones that are too long or too short. But maybe we just don't want this soup. Well, I don't know. It certainly doesn't hurt. So I don't have a good answer. I don't know. It's a good question. Okay, so what's in the soup now? We got all these edges. Yeah.
I think the trick is you multiply the right molecules that have the right start and finish node.
Yeah.
And if you do that 1,000 times, then
Oh, we're about to get to that. Yeah, right, right. So what Mark's saying is the next step that's coming up is, well, you'll see. But there's going to be a reason why. Mark's right. The point he's bringing up is the answer to your question, and it's going to come up in a couple of minutes. So why don't we wait, and then that's exactly it, right? All right, so here we go. We got a test tube. Woo! You got your DNA, your water, your salt, your glue. How do you pronounce that? Ligase. That's the glue. Okay. For a graph of about 10 nodes, this is about a 20th of a teaspoon. Okay? It's a teeny bit. It's very small. If you have a graph of like 20 nodes, this gets very, very big. And if you have a graph of like 70 nodes, this gets to be the mass of the Earth. You have a lot of DNA. That's an issue in this algorithm, obviously. You get this explosive need for a big pot, and you can't do it. But there are methods to try to avoid the explosive need for lots of DNA. So I'm telling you in advance that although the time is going to be very fast, because the time will be done in parallel here, the need for actual DNA material will get large very quickly, so that we still won't be able to solve very large instances without coming up with a better method. So let's review. In here is the DNA, water, salt, and ligase, and there's lots and lots of copies of each of the edges and of the complements of the nodes. There's tons of them. I mean, 10 to the 11th, 10 to the, I mean, big amounts. Lots and lots of copies. All right, so now let's think. What's going to happen? They're all swimming around. What kind of connections do we expect to happen? And in answering this question, I'll actually put a graph up on the board so we can ask ourselves what kind of things might show up. I got A, B, C, D, E, F. Start and finish. I know there's two F's, but one's capital and one isn't. Okay, that's my graph. It's got a bunch of edges in it. I got a bunch of nodes. I've converted it now to a soup of DNA. There's many copies of each edge. There's many copies of each of the node complements. There's a special small s and a small f for start and finish. And they're sitting in there. Let's describe what might connect together. Give me some examples. Okay, so this collection can go together, where you would have AB, BD, DF, where the overlaps represent the gluing of the complements, and that's sitting around in the soup. Right? Doesn't have to start with the start, doesn't have to finish with the finish. What else? What are other examples? So the point is, now that we've done this, we are not getting Hamiltonian paths sitting in the soup. We can't just look in the soup and see, okay, what's left? Is there anything there? Because there's tons of stuff there, and they don't have to be Hamiltonian paths. One example is it doesn't start with a start, doesn't end with a finish. What else can go wrong? S, A, E, F, F. Starts at the start, starts at the finish, and it's too short. It doesn't go through all the nodes. Okay, so one possibility is it doesn't start with a start and finish. Second possibility is it starts with a start and finish, but it's too short.
We could get cycles too.
Can you get ABC?
ABC, ABC, ABC.
You can certainly get ABC. And then what can happen?
ABC would connect.
Right.
Oh, wait a minute.
Oh, well, you could if I had drawn the arrow the other way, but you can get cycles. You can get AEC.
Can you get ABC? How do you...
No, you can't get ABC because there's no edge from B to C. That's all.
But there's an edge from C to B, and you're attaching the ends of these DNAs.
Yeah, but these things are not, these edge things are not symmetrical. So if there's an edge, when you have an edge CB, and you have C on the right end, on the end of your strand, you can connect it to a B. Well,
How the world doesn't know.
Yeah, I guess yeah, you're right. It's completely symmetrical. You're right, Sam.
Because you take the last 10 and the first 10 of each.
Oh, wait, no, it is. Here, let's think. There's C on the end, and that means the C has the last 10 things from C. Last 10 from C. This is the edge CB. And here's going to be the first 10 from B. Right, so BC is going to be different. So the edges are asymmetrical. And you couldn't get a BC connection. You can get only a CB connection. Okay. But we can get cycles, though. We can get AEC. Well, that's just the case of another one that's too long or too short. And now we've got has duplicates in it. We need a way to pick out the good ones. And we're going to do this in 2 phases, ruling out the bad ones and multiplying the ones that have a chance to be good. There's one situation that nobody's mentioned that's probably the one that can easily trip you up the worst. It is completely possible to start at the start, end at the finish, have the exact right length, and it still not be a Hamiltonian path.
Because you have a cycle twice.
Right. So let's do an example of that. For example, SAEC BDFF. Is that a Hamiltonian path? SAEC BDFF. That is. But you can have another one the exact same length, SAEC AEFF, and that isn't. So it's not enough for us to just look at the things that have start and finish on them and to make sure they have the right length. That's not enough. So if you had some magical way of figuring out the DNAs of a particular length of bases, and you had a way of identifying what they started with and what they ended with, you still couldn't pick out the Hamiltonian paths. So we need that and more. But luckily, biologists are very clever, and they've got all sorts of ways of figuring out just what we need. We're actually going to pick out things that start with start, end with finish, have the right length, and have every single vertex in the graph appear exactly once. All right? And that's what we have to... Yeah, sounds promising, right. All we got to do is figure out a way to do that in a test tube. And not have too many errors in doing it. Okay. Polymerase chain reaction. Anybody know anything about this? PCR? Sham, you know about this?
It's basically
What does it do?
It just makes copies of one thing explosively in an exponential way. So you give it one sequence and then give it all the raw material and make that over and over and over again.
Okay, so what we're going to use this for is we're going to say, look into this soup, do me a big favor, and make lots and lots of copies of any path that starts with the start node and ends with the finish node. You give it a template. You say, I want it to start with this, end with this. Look for any strands that start with this, end with this, and copy them. And it does it fast. And boom, you've got way more of those than you have the others. Okay, so that's step one.
At this point, have we put our ligase in yet? The fixer that...
It's all glue. Yes, the fixer's in there. Right.
So it's not breaking up the others.
Right.
And reassembling.
Right. They're all glued together. Now you have a set of strands that represent paths. Actually, they represent walks because we can have cycles. And the
You're also doing a length. So this is a start, a finish, and a length.
No.
Just start,
No.
finish.
It's just you can't tell it the length. Right. You can just say match patterns. Right. But this is kind of an important point. The less you know about biology, the more clueless your attempts to do this stuff are because you don't know what you can do. I mean, you really need to know. You really need to have some collaboration with someone who's an expert on one side and someone who's an expert on the other side. And I think that's one of the nicest things about this research because it really lets scientists talk to one another, and they rarely do because they don't have to. Now they have to, so it's worthwhile. I think just on that, just for that, it's worthwhile, this research. All right, so what we're going to do is duplicate many, many times all strings starting with S, ending with F. I don't care what's in between. And that's what Mark was saying before. That's one of the reasons why we identify these with all 20 at the beginning uniquely. Is so now we can say, give me things that start with these 20 and end with these 20. And I know for sure that I'm going to duplicate just those. Instead of by accident, happening to duplicate, ones that happen to start with the last 10 of these and the first 10 of the next, that might have matched some other one by some improbable way. Well,
you're going to have other big problems if that happens. So.
Yeah, I guess. Well, we're going to have problems all on the way anyway. But you're duplicating all the strings, start and finish.
What's that process called again?
PCR.
PCR. Like PF flyers. Run faster, jump higher.
Or my time.
It's got nothing to do with this anyway. Duplicate all the strings. You got this big soup now. You got lots more things that you care about than you don't care about. And that raises the probability that we're going to find these things. So things are looking up. But we still have tons of stuff that don't match Hamiltonian paths. There's lots and lots of these things that start with S, end with F, that are not what we want. So first stage, multiply all these, so we've got a lot of the SF ones. Second stage, that's stage number 1. Stage number 2. We're going to take out the ones that are too long or too short. We're going to take out the ones that are the wrong length. Okay, so pick out the strands of length 20. Well, that's easy to say. So Sham seems to know a lot about this stuff. Do you know how you pick things out of certain lengths?
You probably run them in a gel, physically measure the length.
Right, exactly. You make this little gel, and you charge one end, and you let the molecules run through like they're having a race. And the small molecules go faster than the big molecules. And you do this in a very quantitative way, so you know molecules of a particular length after a particular time will be right here. It's not like they can train and get faster. You know that you time your watch and you pull them all out, and there they are. All right, so that's how we pull out things of a particular length.
Where did length 20 come from? Why not?
That's that's just wrong. Of length of length whatever the. Thank you, Michael. That's just a careless mistake. You're pulling out things that are length the number of nodes in your graph. Okay.
Now, the fact that the start and the finish are 30 instead of 20, does that mean they count as 1.5?
You'll adjust.
Yeah.
So we'll pull out length 9 instead of
Yeah.
8.
Yeah, pick out the strands of length n where n is the right number. Yeah, you're 100% right. You do have to adjust. It's not simply 20 times the number of nodes we have. It's that plus.
Well, these nodes are nodes now, right? Because they complement a complement.
Every node.
Yeah, but they're longer. The ones in the end are 30. The start and finish are longer.
I thought it was the start X. The glue was longer.
No, the start x and the x finish are edges.
Yeah. And
Those are 30.
Those are
They're
30.
each 30. Every single pair.
Except for
You
those,
use
it's
a-
20.
Every single pair is 20, except for these, which are 30. And the glue is just overlapping them on top. So,
But no matter what, you're using every bit of every node once.
no, we're not using.
You're using all of start, all of finish, all of A, all of B, all of C, all of D. So it's just 160, I think.
Yeah,
It's eight
it
nodes.
bounces out. It'll be exactly.
Yeah, you know what?
I'm
I'm sorry. You're right, Michael. You're right. I think it does balance. Yeah.
Because you have to use every bit of every node.
I think you're right. I agree. All right, so you count how long it needs to be. Michael's right. I think it ends up being just a simple multiple of the number of nodes in your graph. And you pull things out of that length. Now, there's some error here. You're going to get some bad fish. But for the most part, you're getting good fish. And there's so many ones that start with S and F that will give you a higher chance of getting the good fish. You duplicated them at the beginning, so you got some chance that when they run through this gel, you're not just getting nothing there. And it's more likely you'll get errors, or less likely you'll find the right one. So we duplicate it so we get lots and lots of possible ways to find that Hamiltonian path. It's like putting a little, fire underneath the non-deterministic part. Say, try them all. And I mean try them all. And that's what you do. So you make sure you try them all. So now, in step 2, we have another test tube. Not the original one, a new one. And this new one is holding all the strands of the right length which came from start and finish. Okay, for the most part. There might be a few that don't have start and finish, and there might be a few with the wrong length. That's why it's probabilistic. Okay, step 3. What are we missing? What's the only case that we haven't handled yet? Right, those funny cycles that might appear, like you can see in this graph. Like the case SAEC BDFF, right. That's not really a Hamiltonian path. So how do we take care of that? We'd basically like to just look at this DNA strand and make sure that it has in it every single node once.
What you named was a Hamiltonian path, SAEC, BDFF.
Oh, I meant to say
SAEC.
SAEC. SAE.
Okay, C-A-E-F.
That's what I wrote down before. SAEC A
E-F-F.
EFF. You keep saying it and saying it, and I don't write it. All right. How do we make sure that doesn't happen? Here's what we're going to do. Actually, you know all the tools, so I'll throw it to you as a puzzle. It's not a new tool. It's something, maybe a teeny new tool, but more or less you know how to do it. How do you find out whether this is happening or whether you have just a unique copy of every node in your string?
AE is duplicated.
How do you check that? How do you check if it's duplicated? I mean, we can obviously look through it and see with our eyes, but we need some way of in the lab doing it. And I don't think there's any way in the lab. Well, actually, there is. There is a way in the lab to take a strand out and read it. But that's very slow. So you don't want to do that with every strand and just check it.
If you throw a complement in and it binds twice, possibly? Or it makes a ring or something?
We do need to use complements. That's the right idea. Yeah. Seth, you have...
Well, you could bind something a specific way to every position, and then you could sort them by weight.
Right, but we can't specifically put the bindings on here. We can only throw it in and let them connect.
You could have a molecule that would bind any specific node, and then something that has two of the same nodes in it would have a different weight, and when you sorted it by weight, you know what they are.
Okay, that's assuming we can sort them by weight quickly and stuff. Okay, that's not the way they do it, but it certainly seems good enough to me from my knowledge of this stuff. Sharon, you had an idea?
What if you put exactly one copy of the complement of each node into it? And with that, and then if you had anything left, if you had anything that wasn't bound to that, then you would have to do.
So that is more or less exactly how they do it. So let's go through the idea. The first thing they do is they take this test tube and they throw in complements of A. Just A. Okay? And they see if it binds with something. And then they fish out all the ones that A binded with, bound with, boined with. How do you do that? You throw in a complement of A, you throw in lots of it, and you attach to it something that's magnetic, and then you run through it with a big magnet, and you suck out everything that's magnetic. You can do it. I don't know how, but they do it. So you throw in a complement with some kind of magnetic orientation, and then you let it bind with any of the strings that it binds with, and then you pull out anything that's magnetic. So now you've pulled out all the strands that have A's in them. Yes?
At this point, though, aren't these series of nodes, aren't they actually now double helixes that have actually been bound together? Isn't that what we produced in the first place?
Yes, that's true, right, because there's...
Because it's those original edges plus those...
Yeah.
That we created, so.
Yeah, so you're saying how can you bind them?
Yeah, what's binding?
What's left to bind? That's a good question.
Well, you can cut the double helix apart again and then throw in a bunch of complements. I mean, I'm not sure that's what they do, but you could do that.
I guess. I don't know the answer. It's a good question.
Break apart all the paths for them, because the helix is what's holding the paths together.
Actually, what happens is once you form the double helix,
Yeah.
the two strands are also connected up. So it's not just a cross. But
Once you form the double helix, then each strand on its own links laterally.
and then you heat it
And,
up.
and then you heat it up, they break apart, and you get these nice strands. Huh.
The bonding across is much weaker.
It's like macrame. It's...
You can remove the complements of the nodes that we use to hook it all together once it has...
Yes, that's what Seth is implying, and Sham is saying that that's realistic, and I imagine that's a good answer to your question, Kevin. I don't know the answer, but I imagine that's reasonable. That once you get all these things, you can get rid of the original glue, remove it, and now the substrate is all glued together, and it's okay. So then you can put these binders in again.
So now the only raw material that's in there is the A that we just added?
Right. The complement of A with all these possible paths. And then we fish out with a magnet all these paths that have A's in them. Well, that's fine. So now I've got all the correct length paths, starting with start, ending with finish, that have an A in them.
You do that with each node?
And then I do that with B, and I do it with C, and D, and E, and capital F. I check to make sure that when I'm all done, after this, first I take all the ones that have A's, then I throw B in that new solution. I take out all the ones from there that have B's. I don't need lots of test tubes. I can wash the other one out. I take out all the ones with C's. I take all the ones with D's. I take all the ones with E's and F's. When I'm all done, if there's anything left in that last test tube, it's a strand that starts with a start node, finishes with a finish node, and has an occurrence of every one of the other nodes in between exactly once. So it's the right length, starts where I want, ends where I want, and doesn't do anything twice, so there's no cycle. So I'm guaranteed it's a Hamiltonian path.
How do we get it to be exactly once?
Because we've got all the nodes.
Because we're first throwing in complements of A, a whole bunch of them into the soup, and then we fish them out with a magnet. So now I have all those strands of correct length that have an A in them. And now I throw in complements of B, and I fish them out again. So now I have all the strands of the correct length with A and B in them. And I do this once for every single node, so when I'm all done, I know that every single one of the nodes appears exactly once, and I already knew they were the right length, so I know they can't appear more than once or less than once. That gives me if and only if.
So we're not checking for duplicates. We're actually back to the...
Exactly. We don't check for duplicates because presumably there's no lab technique that does that quickly, but we check for the existence of a single one, which we can do fast and we do that n times. Now this is done in parallel, so this is being done with millions of strands all at the same time, and you fish them out all at the same time. And if we have one single strand in the last test tube, we say, yes, there's a Hamiltonian path, and we send that strand through the sequencer, the only slow part of the whole process, which actually scans the bases and prints them out on a screen, and that tells us the Hamiltonian path from the original graph. If it's just filled with salt and water, we say no. Yeah.
What kind of time are we talking for each of these steps?
So that's a good.
You say they're fast, but does fast mean 30 seconds or a day?
No. As fast as you can put the stuff in and throw it out.
Because the gel, whatever, electrophoresis, whatever.
Well, that'll probably take you an hour or so. But putting the stuff into the test tube, within a minute, it's all done.
Yeah, but the gel's going to take
about an hour.
Okay, but yeah.
Sham says the gel takes about an hour. This step takes about an hour, the right strands of length. This is, the last step is all the complements one at a time. That takes a few seconds for each one. Fishing them out with a magnet and preparing the complements with the magnetic part to begin with probably takes some preparation time in the lab. From what I read, the very first time they tried to do this, not only were there tons of errors, but it took about a week or two to get the whole thing done. Now I imagine you can make it go faster when you're all ready, and take a day if you're really there. Okay, but this is for a small graph. Yeah.
Suppose you made the complement to AE, a specific sequence AE.
Mm-hmm.
Would that bind in two different places to your? Would the first AE bind to the first AE and the second, and there'd be a loop of DNA that was unbound in between?
Yeah, if you throw in complements of AE onto that sequence, it'll bind to both places. It can distinguish between this AE and that AE.
Right.
So we could have a loop, a single strand of DNA somewhere in between.
No, AE won't bind itself to AE because they're not complements of each other.
I'm asking you to give the complement of AE.
Mm-hmm.
So my complement will bind to the first AE.
Oh yeah, then what you have is a loop sticking out.
Right.
Yeah. So it'll bind it.
So it binds here, and you get a loop.
And that C will kind of pop out and stick out into the solution.
Small patches rather than a...
Right. It's
Yeah.
a sequence of complement AE, and you throw it in there.
Right.
Bind to the first AE and the
Right.
last AE.
Of course, we don't ever do anything like that because we're only sending in single complements of A's all separate from one another.
I was just thinking of an alternative way of doing it, not necessarily better than yours.
Yeah, this isn't mine. This is, I understand what you're saying. You want to send in these two combined in a complement way and get a loop and
for duplicates if there's anything sticking out.
Right.
That could be done with AA. Any node itself could be duplicated. AA would make something stick out.
Well,
yeah.
You don't want to do that.
All right, so let's talk about how long this takes, and maybe people who know more about the biology can volunteer information and talk about just a little bit what the issues are.
It seems like it has this sort of whole notion of being probabilistic, and maybe you still have some wrong stuff at the end. But if you wanted to take extra time, you could purify it and redo a lot of these steps over again and really get your chances of
Right. Right, and you could repeat the experiment many times with the same starting point and make the chance of you getting the wrong answer as small as you like. You can't guarantee certainty any more than I guess you can guarantee certainty in a computer either. There's always a chance there's an error. But you can guarantee certainty probably to whatever extent you want as long as you're willing to spend the time and do it as many times as you want. Whatever the percentages of doing it once, you can do it again and again and make the percentage of your correct answer that much higher. That's true. So the probabilistic part of it isn't, I think, so bad, except that what if the errors are bad and the chance of you getting the right answer is 50%? I mean, then it's a complete waste of time. So you got to assume that we have as much control in the lab, more control in the lab than just complete randomness, and that these techniques are fairly good, and then it works. How long does each step take? Making up these strands takes some time. Throwing them in the soup and letting them connect, that's the part that's non-deterministic analogy. You're throwing billions of these strands into this soup, and they all connect up at the same time. You're checking them all virtually at the same time. And that's what you can't do in a computer. That's the part we're really leveraging. Chris?
But you were saying the more nodes you have to deal with, the more DNA you have to throw into your mix.
Yes.
So
if we think of this as the time analogy, that's the space analogy.
Okay.
Space explodes.
But it also would take time. I mean, you have to assemble all those DNA strands.
Like, assuming everything is ready and you throw it in, the process itself is the process for finding
If we have 2,000 nodes, which is a pretty hard problem to do the Hamiltonian path on, we still only have to assemble 2,000 DNA strands and maybe 2,000 squared edge DNA strands. Right? That's not the bad part. It's just that we have to duplicate them 10 to the 25th times. So it's not the preparation that takes time. It's the fact that we physically need to make so much of it that there's more DNA in the experiment to make the probability work than there is, kilograms on the Earth. 10 to the 25th kilograms of DNA or something.
Still, it seems kind of like it's more like a massively parallel computer where the processors are just ridiculously cheap, and you can prepare yourself a parallel computer with as many processors as you could ever need to solve a given problem. They just happen to be free.
Right.
And then you set it loose.
Right. So Chris's question is, why can't you just simulate this with a computer in some sense, where the computer just does these matchings and you just have them all, because all these things can be done in parallel as long as you have enough data thrown at it. So if you have a massively parallel computer, it can in some sense simulate this. And I think that's true, except that we just have the computer already, and it's really small and very efficient, and we just use it rather than build one. I'm not sure that we have the capability of building one in the massively parallel way that our body can already do it. But in principle, people are working on just that. People work on massively parallel machines all the time and trying to build them and make them better and faster and larger. But we're still talking about the connection machines are what? They're, I don't know, on the order of tens of thousands of processors, not on the order of millions of processors. So it's still just theoretical, the idea of really modeling this with a real machine.
Not polynomial space then? Sorry.
Right, it's not polynomial space. The space grows like crazy. And that's partly because of this algorithm. It's not endemic to this method that the space has to grow exponentially. It turns out to guarantee good results in this algorithm, you need to duplicate your DNA enough times so that the necessary DNA gets too big. And the exact amounts you have to duplicate it have to do with the errors in the experiments. So practically this particular one doesn't work for more than a dozen cities or a dozen nodes.
And we can solve that on a computer now.
Right. Right. This is not a competitor to the best engineering tweaks we can do with our algorithms on a regular machine. And that's why it hasn't really hit the big time news. Here it is, the new great idea, and everybody talks about it in the New York Times. Did you hear about the molecular computer? It still gets there, but it's still more like, well, here's a curiosity. But the reason it's interesting is because in principle it could get there. In principle, you could get a better algorithm that the space doesn't explode. You could get better lab techniques which make the probability very, very high even without making 10 to the 12 copies of all these things. You might be able to get these algorithms to work for other problems that have been forbidden, well, not forbidden, for can't think of the word.
Forsworn.
That you can't do well on a computer. Forbidding. That's foreboding. For nothing. All right. Question, yeah, Chris.
So what would make this, like what sort of time constraint would make this not? But if it were a function, if how long this whole process took were a function of the number of nodes itself?
It is. It's a linear function.
Right, because
you have to make every DNA molecule, and that's proportional to the nodes. Actually, it's proportional to the edges. It's a linear time algorithm.
Is that okay? Though I thought that with the non-deterministic machine, that this part had to be.
No, that's okay, Chris. Non-deterministic machine is still non-deterministic polynomial. It includes the time it takes to generate the guess and the time it takes to check the guess. And that's basically what we've done here. We've generated the guess in linear time. They all get checked at the same time, so all we have to do is measure the time it takes to check one of them. So it's really very much a way of turning the non-deterministic abstraction into reality. So it's okay to count the preparation, and it's okay to count the checking time. And what we get for free is we don't have to sequentialize the checking. They all get done in parallel. And notice it's a natural OR. Right? If any one of them work out, we just look. If it was an AND, that's not as easy to model. So, and if it was combinations of ANDs and ORs, it's not as easy to model. Okay, other questions?
I'm confused about the space. When we have this magic non-deterministic machine, or I talked with you last week, aren't we using exponential space? And you said magically no.
No, we don't use exponential space at all.
Well, there are exponential number of magic machines, each one using constant space.
Right.
Now here we've got a real-life non-deterministic machine, and it seems to be using exponential space.
Right.
Is that accidental, and you're eventually going to get it down to?
No, you're just pinning me down
All right.
on my promise that it was really a non-deterministic real machine, but it's really not. In a non-deterministic machine, the only thing we count to measure anything is the time it takes to check one guess and the space it takes to store that guess.
That guess, yeah.
So we count every machine, even the ones that you're thinking of as being massively parallel, and the space and time requirements are that of one of those machines. Here, the time requirement becomes identical to the abstraction,
yes,
but the space requirement doesn't. We actually still have so many multiple copies to make this thing work that we're essentially storing all of it, even though the time is done in parallel.
But that's just a very big constant in polynomial space?
No, it's really, it's exponential.
And is it accidental that it's exponential now? As laboratory techniques improve, we'll get it down to polynomial?
Yes, that's the idea. Right. There's nothing endemic about this process that made that be that way. I mean, you could conceivably do this with just, you know, some very, very small copy of each molecule, which wouldn't exponentially explode, as long as the techniques in the lab were careful enough, and as long as we could analyze the probability. You just basically need enough so that all the combinations would show up eventually. And I don't think that's too many mathematically. I think the weak link is in the lab techniques, not in the mathematical expectation of what would connect up in a random graph.
You're assuming that the template and the original match or don't match on a 10 to 10 basis, but suppose they match on a 3 to 3 basis. You might have two pieces with a space in between because they.
Absolutely.
Am I saying this?
No, you're saying exactly right. That's one of, I think, 3 or 4 different things that can go wrong. We do get some of those things out during this process of screening. We do get a lot of the bad ones out, but things will. We are carrying around a lot of stuff. It really is a soup of stuff, and things that we don't want do get pushed along.
You're going now to have an exponential number of things that you have to check.
If you did take the other half of the strand after they've combined, right, then wouldn't that work out to two strands of 3 lengths, and you would just lose?
Suppose my glue is 20 long, and we're saying that we would like to have 10 here and 10 here to glue these pieces together. But the same glue might attach in 3 places here and in 3 places here, and this is certainly not a correct answer.
But those are not going to be, you're not going to bind, those base sequences aren't going to bind together, so when we decompose the base pair matching, you're just going to get bits, and they're going to be weeded out.
Don't we always have to check these, though?
No, because they're not going to be the right length. They're not going to be...
We check them explicitly in one of these phases. Chris is saying that they would be weeded out in one of these phases.
But doesn't that take an enormous amount of time?
No. The magnet comes down and sucks out all the ones we want, and in the gel phase, they all come running down in parallel, and after a couple hours, we just look at that spot. Right, no, so it doesn't. All those steps are done in parallel. you basically have the equivalent of an exponential number of processors to work with you.
And the probability of correct matching is much higher than the probability of partial matches. So the number of such errors you get is much lower.
You mean you'd expect a higher probability of longer matches than shorter matches?
Shorter
Yeah.
matches. That's the way it works.
See, I only have to have 3.
No, it's a dynamic process. It's going to stick together. And if all of them stick together, you have 10 bonds formed. So the energy that you now require to break all 10 bonds is much higher. But if 3 of them stick together, then you have only 3 bonds formed. So that will break at some point, or it may not break, but its chance of breaking is much higher. So they keep going back and forth, and after a while they settle.
So they conform around a little bit, and then they decide on the minimum, on the most stable energy configuration for the collection of the soup, and then they stay that way.
To keep them from being bound in just one region, I am concerned that possibly when we put in our different elements, that they won't completely diffuse and have a mixed, completely well-balanced mixture, and maybe, you know, AE happens to be next to each other, and we're going to bind up all our AEs before they ever get in the presence of a B.
Oh,
for example.
Well.
And maybe if we've got a really small sample that maybe only does 4 nodes, fine. Maybe it's small enough that they can diffuse. But if we're doing one of our...
The real answer to your question is that you have so many of them that the chance of that happening is teeny. You have so many copies that they're going to move around and hit the other places and not just get stuck in their own teeny weeny copies of these useless paths. So there's a very high chance that they're sooner or later going to get to and the wrong answer is that you just mix it with a spoon before you start.
But what Shai said makes a big difference, that even if they do bond just with two bases or whatever, if once you do stir them around, if they find a better match later on, they'll pull away.
Yeah.
But A and E would bond completely, and then...
But Doug's just saying it's completely possible that you throw in all these copies of this edge, and it bonds up in all these paths that are not Hamiltonian paths, and now they're all used up. And the AE that you want in the Hamiltonian path isn't around, and you blew it. And that's going to happen much more often the fewer copies you put in. It's also going to happen much more often when your experiment is lousy. If you really have these things mixed well to the point where you expect them to uniformly distribute in a better way, then you can put in fewer copies. So there's this trade-off between the mathematical analysis of what's just the random way you expect things like this to match together, assuming they will be randomly distributed, and the way they really end up getting distributed. And I'm not sure of the details of that. That's all. That's as much as I can really say. But I think you're looking right on the issues. I mean, that's exactly what people have to work on. So there are other problems you can do with DNA. The maximum clique problem, there's a way to do. Mark, did you find anything on the web on this stuff?
Not really. It wasn't detailed enough.
So it's hard to... But you remember there was an article you said in Scientific American a few years back? And it described the maximum clique method and what else?
And Hamilton cycle.
And this one, yes. And Hamiltonian path. Yeah, okay. So there's still research going on here, and it's mildly controversial because the question is it just, you know, kind of fun and goofy, or is this really cool? Because if you really got it to work well, and it wouldn't explode, and it could ever outperform a computer, the best engineering tweak someone could do, that would get real press. That would be very interesting. And everybody would start throwing money and effort and time right in this direction. So the second the first successful breakthrough that really like wins out over a computer with this kind of model comes through, there's going to be a lot of attention to it, and it will become a much more flourishing field. Or it could just fade and stay on the burner for a long time. Nobody knows. Okay.